When we think about line integrals, we usually think about measuring some total effect along a whole path. But what if you don't care about the whole journey? What if you only want to measure the motion in one specific direction? Like, say, just the work done pushing something forward, even if the path itself is all curvy and complex. Well, that's exactly the kind of line integral we're going to break down today.
Imagine this. You're pushing a little cart along some winding garden path. At the same time, maybe there's a strong wind blowing from the side. Now, you're not interested in the total effort or the wind or anything else. You just want to know one thing. How much of your work went into just pushing that cart forward in the X direction? This is precisely the kind of question this type of integral is built to answer.
Okay, so this right here is the absolute heart of the matter. The line integrals you might have seen before, the ones with ds for arc length, they measure the total effect along the entire roller coaster ride, every dip and turn. But the integrals we're looking at today with dx and dy, they let us be picky. We can totally isolate and measure just the horizontal push or just the vertical pull. It's a subtle difference, but it's an incredibly powerful tool, especially in physics and engineering.
So how in the world do we actually calculate these things? I know the notation can look a little scary, but the whole process really just boils down to a super simple 3-step recipe that you can use every single time. Let's walk through it.
This is what you'll typically see in a textbook. You've got some function p that's affecting the x direction and another function q that's affecting the y direction, and we're integrating them along some curve c. The challenge is pretty obvious, right? You've got x's, y's, dx's, and dy's all mixed together. How do you solve something with so many moving parts? The trick is to translate all of it into one single common language.
And here it is, our 3-step recipe. It's always these 3 steps. First, we parameterize. This is the key that unlocks the whole thing. We're going to rewrite our path using a single parameter, t. Second, we substitute. We take everything, x, y, dx, dy, and swap them out for their new t versions. This magically turns a messy multivariable problem into a standard Calc 1 integral. And finally, we just solve it. That's it. Parameterize, substitute, solve. Let's see it in action.
All right, let's put our recipe to the test. We'll start with a classic example, a path along a nice familiar curve, a parabola. So here's our problem. We need to evaluate the integral of 2y dx plus x dy, and our path, c, is the curve y equals x squared, starting from the origin, 0, 0, and ending at the point 1, 1. Step 1. Parameterize. Now, since the curve is already given to us as y in terms of x, the easiest possible thing we can do is just let our parameter t equal x. So if x equals t, then the equation y equals x squared just becomes y equals t squared. Easy enough. Then we find the derivatives. The derivative of t is just 1, so dx is dt. The derivative of t squared is 2t, so dy becomes 2t dt. And since x goes from 0 to 1, our parameter t does the exact same thing. Perfect. Everything is now in the language of t.
Now for step 2, substitute. We just go through and replace every single piece. The 2y becomes 2 times t squared, the dx becomes just dt, the x becomes t, and the dy becomes 2t dt. Doing a little bit of algebra there gives us a much friendlier looking integral of 2t squared plus 2t squared.
And now for the easy part. Step 3. Solve. We combine those terms to get the integral of 4t squared. We find the antiderivative, which is 4/3 times t cubed, and then we just evaluate that from our bounds of 0 to 1. We plug in 1, which gives us 4/3. We plug in 0, which gives us 0, and our final answer is just 4/3. See? You just follow the recipe.
Okay, that was a nice smooth curve. But what about a boring old straight line? Well, the process is exactly the same, but how we parameterize it looks just a little bit different.
For our second problem, we're integrating y squared dx plus x dy along the straight line segment that connects the point -5, -3 to the point 0, 2.
Step 1. Parameterize. Now for a line segment, there's a standard formula we can use. You take your starting point, which is -5, -3, and you add t times the direction vector. The direction vector is just the final point minus the initial point, which gives us 5, 5. So x of t is -5 plus 5t, and y of t is -3 plus 5t. The derivatives are just constants this time. dx is 5 dt, and dy is also 5 dt. And to trace the whole line, t will go from 0 to 1.
Okay,
Now we substitute all of that back into our integral. And I'll admit, it looks pretty messy at first, but trust the process. When you expand everything out, distribute your constants, and combine all the like terms, all that initial complexity just melts away, and you're left with a clean, simple polynomial that's easy to solve. That's the real power of this method.
After we integrate that polynomial and evaluate it from 0 to 1, we get our final answer, -5/6. And yeah, line integrals can totally be negative. A negative result could mean that, on average, the force field was working against our direction of motion.
All right, for our last example, let's look at something really fascinating. A path that starts and ends at the exact same place, a closed loop.
Here's the task. Evaluate the integral of -y dx plus x dy. And our path is the unit circle, which we're going to travel around once, counterclockwise. Oh, and see that little circle on the integral sign? That's just special notation to tell you, hey, this is a closed path.
Step 1, as always, is to parameterize. And for the unit circle, this is the classic parameterization you'll want to remember. X is cosine of t, and y is sine of t. The derivatives are pretty straightforward. Dx is negative sine of t dt, and dy is cosine of t dt. And to go around the whole circle one time, t needs to go from 0 all the way to 2 pi. And this is where the magic happens. When we substitute everything into the integral, we get negative sine of t times negative sine of t, plus cosine of t times cosine of t. That simplifies to sine squared t plus cosine squared t. And what's that? It's only the most famous identity in all of trigonometry. It's just equal to 1. The entire complicated integral just collapses into the beautifully simple integral of 1 dt.
And the integral of 1 from 0 to 2 pi is, of course, just 2 pi. That's our final answer. But there's a much deeper meaning hidden in that number. This is so incredibly cool. Think about it. The area of a unit circle is pi. Our answer is 2 pi. That is not a coincidence. It actually turns out that this specific integral, the closed loop of -y dx plus x dy, is a well-known formula for calculating twice the area enclosed by any simple closed curve. It's this beautiful, unexpected bridge between the world of line integrals and pure geometry.
So what are the big takeaways here? First, remember that these dx, dy integrals are all about measuring components, just the horizontal part or just the vertical part. Second, that 3-step recipe, parameterize, substitute, solve, is your universal key. It works every time. Third, and this is so important, the path you take matters. As we saw, different paths between the same 2 points can give you wildly different answers. And finally, sometimes these abstract calculations hide these amazing geometric secrets, like the area of a shape. Which really leaves us with one final fascinating question. We've just hammered home how critical the path is. But what if it wasn't? Are there special vector fields out there where the work done to get from point A to point B is exactly the same no matter what crazy path you take to get there? Well, the answer is yes. They're called conservative fields, and they're a huge topic for another time. Thanks for watching.